In this video you will be introduced to the central role statistics play for data science tasks. The video belongs to the introductory section of educational module, Statistics for Data Science. Statistics as a major part of data science. As we already discussed in the Introduction to Data Science course, statistics is one of the three major domains that data science is based upon. The other two are computer science and domain/business knowledge. Statistics is one of the most important disciplines that provide tools and methods to find structure in and to give deeper insight into data, and the most important discipline to analyze and quantify uncertainty. Statistics is a broad scientific domain, which deals with the study of data and is widely applied in numerous fields such as life sciences, weather, the stock market, retail, insurance, marketing and education. Statistics provides the methodology for making conclusions from data. It gives different methods to gather data, analyze them and interpret results, and is widely used by scientists, researchers, and mathematicians in solving problems. Statistics is synonymous with data-intensive activities such as collecting, processing and interpreting processed data. Statistics helps to obtain information from numerical and categorical data such as blood group, marital status and more. When it comes to data-related tasks, statistics can play a significant role because it helps to decide the type of data required for a given situation, to organize and summarize data, to analyze and draw conclusions from data, and to assess results and evaluate uncertainties. Moreover, statistics offer us methods for planning and conducting research, exploring and summarizing data, and making predictions and inferences using the phenomena represented by data. A role of statistics in data science is often underestimated. This stands, in particular, for the areas of data acquisition and enrichment, as well as for advanced modeling needed for prediction. To become, though, a successful data scientist, it is important to have a basic background in statistics and the related mathematical concepts, as they are the building blocks of machine learning algorithms and therefore necessary for anyone who wants to know how and when to use them. As Josh tweeted, "Data scientist is a person who is better at statistics than any programmer and better at programming than any statistician." In summary, the bond between data science and statistics is strong, to a degree that makes the two practically indistinguishable in many cases. Statistics is a major tool for data science, and data science is a wide domain where statistical methods are deployed as essential components. When dealing with data science tasks, some key statistical concepts are necessary. Population is the set of sources from which data has to be collected. In other words, the population is the entire set of individuals or objects of interest, or the measurements obtained from all individuals or objects of interest. The sample is a subset of the population. The variable, also called a data item, is any characteristic, number, or quantity that can be measured or counted. A statistical parameter or statistical model or population parameter is a quantity that indexes a family of probability distributions, for example, the mean, median, etc. of a population. It is a numerical value which summarizes the entire population data. An experiment is a planned activity whose results yield a set of data. A statistic is a numerical value which summarizes the sample data. There are two types of data analysis: quantitative and qualitative. Quantitative analysis or statistical analysis is the science of collecting and interpreting data with numbers and graphs to identify patterns and trends. Qualitative or non-statistical analysis gives generic information and uses text, sound and other forms of media to do so. Qualitative research is typically unstructured and exploratory in nature. Typical techniques for data collection include interviews, focus groups, observation. In data science we typically use quantitative analysis. Quantitative analysis aims to objectively measure the topic at hand, using mathematics and statistics. Typically we analyze raw data collected for qualitative analysis with the help of a spreadsheet software program like Microsoft Excel, or a statistical package like SPSS. To facilitate this type of analysis, the data must be in a structured format. Let's say you want to know the average age of all players in the Milwaukee Bucks 2019-20 team roster. To conduct this research you must collect the required data, i.e. all players' age, and for this purpose you can either conduct a survey and call up each player on the phone to ask them, or you could physically find them and ask to see an official document stating their birth date. Both would be examples of primary research, but in this case, as in many other cases in the real world, secondary research is a much more practical option. So you would probably compile the data from NBA.com. Thus quantitative research can come in many forms, including surveys, observation, experimentation, and secondary research. Statistics are categorized as either descriptive or inferential. Descriptive statistics uses the data to provide descriptions of the population, either through numerical calculations or graphs or tables. It helps organize data and focuses on the characteristics of data providing parameters. Suppose you want to study the average age of participants in a lab experiment. In descriptive statistics you would record the ages of all participants and then you would find out the maximum, minimum and average age. Some other measurements in descriptive statistics answer questions such as, how widely dispersed is the data? Are there a lot of different values? Are many of the values the same? What value is in the middle of this data? Where does a particular data value stand with respect with the other values in the data set? Descriptive statistics are numbers that summarize some characteristic about a set of data. They provide you with easy to understand and help researchers get a rough idea about collected data, so later they can do more formal and targeted analyses. Commonly used descriptive statistics include the mean numerical average of a set of values, the median midpoint of a set of numerical values, the most common value among a set of values, the percentage, the frequency, the number of times a value is found, and the range, the highest and lowest value in a set of values. In descriptive statistics we typically calculate measures of center, measures of variability and percentiles. Measures of center, mean or average, and median. The median is the number that divides a given sequence of numbers in half. For instance, if we have the sequence of 1, 3, 4, 8, 9, then the median is 4. When the sequence has an even number of items, the median is calculated as the mean average of the two middle numbers. For instance, if the sequence is 1, 3, 4, 6, 8 and 9, then the median is the average of 4 and 6, which is 5, and in this case the median is not one of the values in the given sequence. Compared to the median describes better the dataset as it is not affected by outliers, a few extremely high or extremely low values in the data set that drag the mean to a very high or a very low number respectively. The typical measure of variability is the standard deviation. The standard deviation is a measure of how spread out numbers in a given dataset are. Its symbol is the Greek letter sigma, and for a dataset with n items it is calculated with this formula, where x hat is the mean value of the sequence. Percentiles is the most common way to report relative standing of a number within a dataset. A percentile is the percentage of items in the dataset who are below the position of the item in question. Another method of descriptive statistics is the graphical representation of data such as histograms, bar graphs, pie graphs and box plots. Let's see an example of percentiles. Take a look at the table below listing the ages of players in the Bucks roster for 2019-20. If we want to calculate the percentile for DJ Wilson's age, we see that from a total of 17 players sorted in ascending order by age, then this player has 14 players below him, which means his age is the 14/17 equals 82% percentile, i.e. 82% of all the players in the Bucks team are older than DJ Wilson. The 5-number summary is a set of 5 descriptive statistics that divide the dataset into 4 equal sections. These 5 numbers are the sample minimum smallest value of the dataset, excluding outliers. The lower quartile or first quartile, 25% of scores fall below the lower quartile value. The median, the middle value. Half the values of the dataset are greater than or equal to this value and half are less. the upper quartile or third quartile 75% of the values fall below the upper quartile value, and the sample maximum largest value, excluding outliers. In addition to the median of a single set of data, there are two related statistics called the upper and lower quartiles. If data are placed in order, then the lower quartile is central to the lower half of the data and the upper quartile is central to the upper half of the data. These quartiles are used to calculate the interquartile range, which helps to describe the spread of the data, and determine whether or not any data points are outliers. The box plot, also called box and whisker plot, is the graphical display of the 5-number summary of a set of data. Box plots divide the data into sections that each contain approximately 25% of the data in the set. These quartiles are used to calculate the interquartile range, which helps to describe the spread of the data, and determine whether or not any data points are outliers. Thus box plots are useful as they provide a visual summary of the data, enabling researchers to quickly identify mean values, the dispersion of the dataset, and signs of skewness. Whiskers upper and lower represent scores outside the middle 50%, i.e. the lower 25% of scores and the upper 25% of scores. The interquartile range, or IQR, is the box showing the middle 50% of scores. An outlier is an observation that is numerically distant from the rest of the data. When reviewing the box plot, an outlier is defined as a data point that is located outside the whiskers of the box plot. Each whisker extends to the furthest data point in each wing that is within 1.5 times the IQR. Any data point further than that distance is considered an outlier, and is marked with a dot. While descriptive statistics describes data using a chart or graph for calculating average, mean, maximum, etc., inferential statistics allows making predictions or inferences from that data. With inferential statistics, we can use data from samples to make generalizations about the population using probabilistic models. Inferential statistics is the branch of statistics that deals with generalizing outcomes from small samples to much larger populations. For example, you might stand in a mall and ask a sample of 100 people if they prefer shopping from physical stores than e-shops. If you decide to rely on that 100 answers, you can use descriptive statistics and present the collected data, e.g. through a pie chart, or based on your sample you could make a generalization about the general population and say that, for instance, 65 to 70% of all shoppers in all malls of the country prefer shopping in physical shops rather than online. Inferential statistics are classified in one of two main categories: estimating parameters and hypothesis testing. Estimating parameters is when we take a statistic from our sample data, for example the sample mean, and use it to say something about a population parameter, i.e. the population mean. Pay attention to the terminology. In the sample we have statistics, in the population parameters. Hypothesis testing, on the other hand, is when we use sample data to answer research questions hypotheses. For example, we might be interested in knowing if sex impacts pupil performance in school, or if breakfast helps children perform better in schools. Statisticians use hypothesis testing to formally check whether the hypothesis is accepted or rejected. In other words, hypothesis testing is used to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for an entire population. To understand the characteristics of a general population, we take a random sample and analyze the properties of the sample. We test whether or not the identified conclusion represents the population accurately, and finally we interpret their results. Whether or not to accept a hypothesis depends upon the percentage value that we get from the hypothesis. In hypothesis testing, the goal is usually to reject the null hypothesis. The null hypothesis is the null condition, no difference between means or no relationship between variables. Data are collected that allow us to decide if we can reject the null hypothesis, and do so with some confidence that we're not making a mistake. The null hypothesis is a statement of the null condition in the population, not the sample. For example, The first formula denotes the null hypothesis that there is no difference in the mean male and female population. This is formally expressed in terms of population, not sample, means as depicted in the second formula. In this formula the Greek letter mu signifies the population mean, that is, the mean of all the males or females in the entire population. However, we only have a sample to work with, so we obtain the sample mean, denoted by uppercase M. The null hypothesis we are so intent on rejecting concerns the population means. Our task is to determine if the sample means are sufficiently different to infer that the population means are different. At a certain basic level, all inferential statistics procedures are the same. They seek to determine if the observed sample characteristics are sufficiently deviant from the null hypothesis to justify rejecting it. How deviant? This is not an easy question and would take a statistics course to explain properly. The ingredients for making this calculation are the same for all statistical procedures: the size of the observed difference S, the variability in the sample, and the sample size. Here is a step-by-step procedure for performing inferential statistics. 1. Start with a theory. For example, TV violence reduces children's ability to detect violent behavior because it blurs the distinction between real and fantasy violence. 2. Make the research hypothesis. For example, children who experience TV violence will fail to detect violent behavior in other children. 3. Operationalize the variables. 4. Identify the population to which the study results should apply. For our case it could be kids in developed nations. 5. Form a null hypothesis for this population. For our example, the null hypothesis can be formatted as in the formula that follows. After formulating the null hypothesis we move on to step number 6. Collect a sample of children from the population and run the study. 7. Perform statistical tests to see if the obtained sample characteristics are sufficiently different from what would be expected under the null hypothesis, in order to reject it. 8. Document your findings. For dealing with step 7, there are dozens of different hypothesis tests, and choosing one can be a little overwhelming. The good news is that one of the more popular tests will usually do the trick. In this link you can see a very useful diagram summarizing several tests for a single population, when to use them and the type of data best suited for each test, either nominal, ordinal, or interval/ratio. In this video, we discussed the central role of statistics in data science and revised some basic statistical concepts, such as population, sample, parameter, statistic, etc. We talked about descriptive statistics, and more specifically about measures of center, variability, as well as percentiles. We saw what is the 5-number summary and how it is depicted on a boxed plot. Also, we talked about inferential statistics and the logic behind estimating parameters and hypothesis testing. After this rather short statistical break, it is time to move on and introduce the R language and find out the features it offers for data science tasks. Thank you for watching.